Good morning, ladies and gentlemen. I welcome you to this session on network technologies beyond 2006. This session is devoted to new technologies needed for building next generation optical networks, which we expect to go beyond the 10 gigabit per second we have today and which we expect to do pure optical switching. There is a small change regarding the speakers we have today. Unfortunately, Mike O'Mahony is not able to attend this meeting, and Kees de Laat will fill his slot. We are very thankful for this. Unfortunately, we will have no talk about optical burst switching. We will start with a talk about parametric amplification and multiple wavelengths conversion in highly nonlinear fibers. It's given by Miroslav Karasek. Miroslav Karasek received his academic degrees on microwave semiconductor devices and optoelectronics in Czechoslovakia and Czech Republic. He's currently a senior researcher at the Institute of Radio Engineering and Electronics of the Academy of Science of the Czech Republic. His research activities are in the area of measurement and computer modeling of active fiber lasers and amplifiers.
Thank you, Mr. Chairman. Good morning, ladies and gentlemen. Can you please switch on my presentation? Okay, so my talk will be focused on parametric amplification and multiple wavelengths conversion in highly nonlinear fibers, and I will present experimental results and results of numerical modeling. My co-authors are Jiří Kaňka, Jan Radil, and Josef Wojtěch. The only one present is Josef Wojtěch here. You probably heard about erbium doped fiber amplifiers, Raman fiber amplifiers. I'm not quite sure if you heard about parametric amplification in optical fibers. There is a big difference between these three types of amplifiers. Maybe I should also mention semiconductor optical amplifiers, which are, however, not based on optical fibers. So parametric amplification is based on third-order parametric processes. These third-order parametric processes involve nonlinear interactions among four optical waves propagating throughout the fiber. And they include third harmonic generation, four-wave mixing, which is sometimes called four-photon mixing, and parametric amplification. All these processes are caused by third-order nonlinear polarization. I prefer this one. So this is a polarization vector, and this is a nonlinear part of the polarization. Epsilon 0 is the free space dielectric constant of the free space, and He3 is the tensor of third-order susceptibility, and this capital E is the intensity of electric field. And significant four-wave mixing occurs only if the phase mismatch conditions between these four waves is fulfilled. That means K1, K2, K3 are wave vectors of these four waves. Omega 1, omega 2 to omega 4 are the angular frequencies of these four waves, and N1 to N4 are the refractive indexes of these four waves at the wavelengths of omega 1 to omega 4. So when this phase mismatch condition is fulfilled, then only and only then significant four-wave mixing occurs. This is an experimental setup which we use for the experiments. So we have a spool of highly nonlinear fiber. Maybe I should explain the difference between the ordinary fiber, which is used for transmission purposes, and highly nonlinear fiber. The difference is in the core diameter and the content of germanium. So the nonlinear coefficient of a standard fiber is about 50 times lower due to the higher content of germanium and smaller core size of the highly nonlinear fiber with respect to standard fibers. So the main purpose is to increase the nonlinear refractive index of this special fiber to achieve this as high as possible four-wave mixing or cell phase modulation in this highly nonlinear fiber. So back to this experimental setup, we use two pumps, or two pump seats in fact. We use distributed feedback lasers as pump seats, polarization controllers because we use phase modulator to remove the backscattering in the highly nonlinear fiber so that we can launch as much as possible power to the highly nonlinear fiber, and therefore we should phase modulate the seeds which we use as pumps. Then we amplify the seeds in high power erbium doped fiber amplifier with an optical bandpass filter. We eliminate the amplified spontaneous emission generated inside the erbium doped fiber amplifier, and then we mix the signal with the high power pump and launch it into, let's say, 1 kilometer of highly nonlinear fiber. And at the output of this highly nonlinear fiber, we take 95% of the output power and demultiplex the signals at the output, and using an oscilloscope, or we can directly connect the, when we use as a signal source a transmitter of 10 gigabit per second system, then we can directly select one of the channels and just to verify if the transmission system is operating. And we can also observe the spectrum at the output of the highly nonlinear fiber using optical spectrum analyzer. For the experiments, we have 4 spools of highly nonlinear fiber. They differ with the zero dispersion wavelengths. This information is important, or this property of the highly nonlinear fiber is important. So we have 3 spools with zero dispersion wavelengths, 1532 nanometers, 1546, and 2 spools of 1560 nanometers. They differ also in length. We have 1 spool of the 1560 zero dispersion wavelengths is 1 kilometer long. The second one is 1.5 kilometer long. All these fibers has slope of the dispersion characteristics range in the range of about 0.19 to 0.92 picosecond per square nanometer per kilometer. And this is the important parameter which characterizes the nonlinearity of the fiber. So this is the nonlinear coefficient, which is approximately 10.5 watt per kilometer. To remove the backscattering generated in the fiber, we modulate the pump seeds. I come back again. We use 2 RF generators which modulate the phase modulator in order to smear the seeds, the wavelengths of the seeds or the phase of the seeds, which supports the suppression of stimulated brilliant scattering. Otherwise, we will not be able to use all the power generated by the EDFA to be launched into the fiber. This is the oscilloscope which we use, which is a 10 gigabit per second sampling oscilloscope with optical heads. And as a source of the signal, we use either DVDM ILEX tester, 8-channel DVDM tester, and we use also 10 gigabit per second signals from multipurpose Cisco 15454 platform. And pump seeds are distributed feedback lasers designed for the WDM applications. This is just an experimental demonstration when we amplified two WDM channels starting at channel number 31 according to ITU grid and ending at channel number 34. And the black lines are the optical spectrum analyzer traces recorded at the input of the highly nonlinear fiber, and the red traces are when the pumps, one pump was on. The pump was at 1560.1 nanometer. So the fiber was the one with zero dispersion wavelengths at 1560 nanometers. So you can see that the amplification was approximately 10 dB in that case. Oops, sorry, I go always the other way around. And these are another 4 channels amplified, but in this case the channels were at the low gain region of the amplifier, so it was channels number 35 to channels number 34. You can, or I should mention that on the other side from the pump wavelengths, this parametric process generates so-called idlers. For those who worked in microwaves, you probably know that some 40 years ago, parametric amplifiers was the only low noise amplifiers in microwave region. In fact, when I was finishing my undergraduate study, my diploma project was parametric amplifier for 4.6 gigahertz early bird satellite. And at that time there were no field effect transistors or hands, so the lowest noise amplifier in microwave region was the parametric amplifier. In fact, the processes used for parametric amplification in fibers and in microwave regions are the same. Just what you need is some nonlinear device. In case of microwaves, it was a step recovery diode. In optical region, it is just a highly nonlinear fiber. So if you launch 2 or more or 3 waves in a nonlinear device, either in microwave region or in optical region, they simply mix together and create idler. So this is the idler wavelengths, which can be used for wavelengths conversion, because if you insert 4 waves here, then you will obtain another 4 waves which are in frequency just on the other side of the pump. The frequencies are simply copied symmetrically with respect to the frequency of the pump. And here I come to multi-wavelengths conversion, all optical wavelengths conversion. So in case, coming back to the schematic diagram, so far we used only one pump for the parametric amplification. If you use 2 pumps, then these 2 pumps beat together, and if the pumps are 100 gigahertz apart, which is the frequency difference of ITU grid, so the ITU grid channels are separated by 100 gigahertz, or maybe for more dense WDM systems by 50 gigahertz. In 1550 wavelength region, it represents approximately, these 10 gigahertz represent approximately 0.8 nanometer difference in wavelengths. So when we have 2 pumps which are approximately 0.8 nanometer apart, then you will obtain spectrum like that. So we still have one signal, but this signal is multiplied into approximately 8 channels which have the same modulation format, or they carry the same modulation information as the signal. So if this signal is 10 gigabit per second modulated, so all these signals and all these idlers will have the same 10 gigabit per second modulation. So you can easily use all these 8 channels which have approximately the same amplitude and quality, and let's say these 6 idlers, because these idlers have already lower amplitude, so cannot be used for experimental transmission. But Another advantage is that all these channels and all these idler are fixed to ITU grid frequencies, to ITU grid wavelengths. If the pumps are, as I mentioned already, 10 gigahertz apart, and if the signal is fixed to ITU frequency grid, then all these newly generated signals and newly generated idlers also are fixed on ITU frequencies. And here are the eye diagrams recorded by this sampling oscilloscope. This is the signal or newly generated signal at the wavelengths of 154932, which corresponds to channel number 35 according to ITU grid. This is the copy of the original signal, which was set at 154772. It was channel number 37. And here are another two eye diagrams. This is a newly generated signal at wavelengths of 155092, which is channel number 32, and here is a copy of 31. Unfortunately, we didn't have a demultiplexer which could demultiplex the idlers, because the idlers are above 1560 and we don't have a demultiplexer for this wavelength region. Just to estimate the amplification properties of this two-pump parametric amplifier, these are the traces of amplified spontaneous emission for different pump powers without any signal. So this is just an amplified spontaneous emission for different pump powers when these are launched into the highly nonlinear fibers, and the pumps were equally divided, or the pump power was equally divided between these two pump wavelengths. And this is another demonstration of this multi-wavelengths conversion in highly nonlinear fiber. In this case, we used different highly nonlinear fiber. This was the highly nonlinear fiber with zero wavelengths, zero dispersion wavelengths at 1546 nanometers. The previous experiments were done with the fiber with zero dispersion wavelengths at 1560 nanometers. And just to demonstrate that the signal can be placed also on the other side than the pumps, because in the previous experiments, the signal was at the lower wavelength side, somewhere here, and here we demonstrate that even if we inject the signal which is at higher wavelength range with respect to the pumps, we can obtain the same properties. These are the idlers in that case, and these are the newly generated signals. What you can see here are the second order signals, and here are the second order idlers. Unfortunately, the level of these second order idlers and second order signal is so low that they cannot be used for multi-wavelengths conversion or multicasting purposes. Now I come to simulations. For the parametric amplification, that means for the parametric amplification with single wavelengths, we have used our own software, which is based on numerical solution of coupled wave equations. And for the two wavelengths parametric amplification and wavelengths conversion, we have used commercial packages, either OptiSym 3.5 from Artis or OptiSystem 4.0 from OptiWave. In fact, in this OptiSystem software package by OptiWave, there is our own beam propagation split-step Fourier transform core implemented in this commercial software. So here are the four coupled equations. I will not trouble you with too much mathematics. These are simply P is the power of the pump, signal, idler, and this is the phase, total phase difference between these four waves between, or three waves in this case, because this is a degenerate parametric amplification. So this is the overall phase. When you solve these coupled equations by a standard Runge-Kutta subroutine, you will obtain results like that. So this is the spectrum of the gain for single frequency parametric amplifier. You can see the spectrum for different values of the pump power. So the gain increases. If you can compare this spectral characteristic of gain with erbium doped fiber amplifier, it is easy to see that the gain is not flat. There is a big difference between the highest gain somewhere here and the lowest gain, which is close to the pump wavelength. So at the pump wavelengths you have the lowest gain, and the gain is not flat. And here is the conversion gain of the idler. So even the idler, if you define the idler conversion gain as the ratio of the idler power with respect to the signal power at the input of the amplifier, so you can see that you can obtain even on the idler side a gain of about 10 dB. So even the idler signals or idlers are amplified with respect to signals. This slide demonstrates the effect of the offset of pump wavelengths from the zero dispersion wavelengths. So you see that the maximum gain remains almost the same. The only difference is that the bandwidth becomes smaller when you move far away or further away from the wavelengths of the zero dispersion wavelengths. So the broadest amplification is obtained if the pump wavelength is as close as possible to the zero dispersion wavelengths. I think I'm running out of time, and these are results of the simulations for two-pump wavelengths conversion. You see that there is a good or reasonable quantitative agreement between the simulation results and the experimental results. These are against the splitting of the pumps. These are first-order idlers, first-order signals, and second-order signals. The signal was somewhere here. And this is another result of numerical simulation which resembles the experimental results demonstrating the amplifying possibilities or amplifying potential of the two-pump parametric converter. So there is no signal in that case, and this is just the amplified spontaneous emission calculated for different values of pump power, starting from 600 milliwatts, this is the green curve, to 350 milliwatts, which is the black curve. Again, the pump power was equally divided between these two pump wavelengths. And, sorry, there should be conclusion. Conclusion is that we have verified that the simulation results based on numerical solution of coupled wave equations and using a commercial simulation packages for two-wave parametric amplification and wavelengths conversion are in good qualitative agreement, and that means that the numerical simulations can be used for design of parametric amplifiers on wavelengths conversions based on highly nonlinear fibers. Problems to be solved is for both cases, that means for parametric amplification or multi-wavelengths conversion, suppression of stimulated Brillouin scattering, because you need to phase modulate the pumps in order to suppress the stimulated Brillouin scattering, otherwise your pump power will not be fully utilized for parametric processes. And another problem is elimination of amplified spontaneous emission generated within the erbium doped fiber amplifier. And honestly speaking, I don't think that these parametric processes will ever be used for parametric amplification, because the disadvantage which you probably can realize yourself is that you must first amplify your pumps, and which means that you must have powerful amplifier operating at the wavelengths of your pump. So why should I use parametric amplifier in the 1550 band if I can use EDFAs? And I can use Raman amplifiers at any wavelength if I have suitable pump source. So I don't think that parametric amplifiers as that will ever be used for parametric amplification. Maybe for multi-wavelengths conversion, because you can realize that if you would like in future use all optical multicasting, that means do it in the optical domain. So this is the way how to multiply your, let's say, 10 gigabit per second, but it's equally possible to do that at 40 gigabit per second, just using two pumps which are one channel apart. That means either 100 gigahertz or 50 gigahertz apart. And if your signal is locked to ITU grid, then all the newly generated signals and newly generated idlers will also be fixed to ITU frequencies. So you can simply send them to whatever customer you want without needing to do it in the electrical domain as it is done so far. So that's my conclusion. Thank you for your attention.
Thank you very much for this interesting talk. Do you have questions on this?
What was the signal-to-noise ratio before and after?
You can easily measure that using optical spectrum analyzer, but for us the simplest method how to verify the usability of the newly generated signals was to send them over an 80 kilometer of standard single mode fiber. And we did that with the newly generated, all 8 newly generated signals, and it was possible with the Cisco 15454 platform to receive error-free all the 8 channels which had approximately equal level. Unfortunately, not having the demultiplexer at the idler side, for the idler side, we were unable to do that for the idlers, generated idlers. So it will be easy to measure the signal-to-noise ratio, but we did not do that. But the proof for the usability of these newly generated signals was just to send them over an 80 kilometers of standard single mode fiber. At that length you don't need any dispersion compensation because the Cisco platform is can survive this dispersion, chromatic dispersion of 80 kilometers fiber without any dispersion compensation, so it was still operating.
More questions? If not, then I thank you again. Our next speaker is Klaus Grobe. He will talk about 40 gigabit per second techniques for metro and regional applications. Klaus Grobe received his academic degrees in telecommunication engineering in Germany. Since 1988, he works on fiber optic transmission. He was designing DWDM backbones for German and European operators and joined ATFA later, where he's now responsible for system consulting in Northern Europe. Now we try to get him wired.
Okay, thank you for the introduction and hello everybody. This talks about 40 gigabit technologies or techniques for metro and regional applications. Why is that interesting? Because for many applications, like for example educational networks, etc., metro and regional systems are to be used rather than the more expensive ultra-long-haul systems. So it's really worth trying to use 40 gig, which is a demanding thing, to use 40 gig with lower cost or maybe even low cost metro and regional systems. The outline of my talk is I will say a little bit about the transmission constraints. Then there's 1 or 2 slides on 40 gig applications, because to be honest, there aren't too many. I will show some slides with the different approaches as how to transport 40 gig, and then I will also show our solution. So with 40 gigabit per second, there are lots of transmission constraints, and they got worse, pretty much worse as compared to 10 gig or maybe even 2.5 gig. And some of these were mentioned in the first talk of this session, because, for example, 4-wave mixing, which is the effect behind parametric amplification, is a constraining effect for transmission. But there are others. There are linear and nonlinear effects, and amongst the linear effects, there is, of course, attenuation, which via amplifiers leads to noise. There is also chromatic dispersion, polarization mode dispersion, and all these effects are getting worse as compared to 10 gig by some dramatic factors. For example, chromatic dispersion is getting worse by a factor of 16. So the dispersion allowance of a transmission system decreases by a factor of 16 when going from 10 gig to 40 gig. The maximum reach without regeneration decreases by a factor of 16. Similar with polarization mode dispersion, which may become the most serious effect, also with attenuation. And on top, all the nonlinear effects, self-phase modulation, etc., are added. So, chromatic dispersion, I already mentioned it, is getting worse by a factor of 16 as compared to 10 gig. So we really have a problem if our transmission systems were designed for 10 gig. Normally, they should not support 40 gig then, unless they are shorter than, say, 10 kilometers or so. So we have to do something, and of course we have to and we can compensate chromatic dispersion. Normally we do so by using dispersion compensating fibers. There are other alternatives, like, where is it? The use of spectral inversion, which was the topic of the first talk. So I could, if I mirror a wavelength into another dispersion domain of the fiber, I could cancel the total dispersion. Theoretically, it's possible, and maybe it can be used. But typically, it's more used that I use by using fibers with plus-minus signs of the dispersion. With 40 gig, in addition to all the dispersion compensation techniques that are already in use, we have to use what is now called tunable dispersion compensation at the receive end. So hopefully we can try to make a 10 gig installation ready for 40 gig as well by placing tunable dispersion compensators in front of the 40 gig receivers. In effect, what is really needed for a stable and simple system, and simplicity is a requirement for Metro WDM, is a 40 gig technology which has highest possible allowance with respect to chromatic dispersion. But it's getting even worse because polarization mode dispersion may now become the most serious effect. I will come to the field audits on fibers. Next slide. We have an additional requirement with the simple low-cost Metro WDM systems, which is, if possible, do not use or do not require PMD compensators. For example, because PMD compensators today are not off-the-shelf components. They only exist in the laboratories. Plus, if it's an existing link which shall be upgraded, placing a PMD compensator would mean opening the fiber, shutting down the link. Not a nice thing for existing installations. So next requirement will be highest possible PMD allowance for the 40 gig technology. This is the result of a massive audit on installed fibers, thousands of them. That was done. The audit was published in early 2005, and interesting is the fibers were installed between 1997 and 2002. So we are talking more or less brand new fibers. We are not talking old fibers. This is relevant. And what they found out is that more than 20% of all installed fibers had PMD massively above all standards, above all ITU standards, massively. There is a serious amount of fibers, these here, that have more than, say, 2 or even 3 picoseconds per square root of link length as the PMD coefficient. Whatever this strange dimension means, it's simply a characteristic for measuring PMD. And the relevant standards say it has to be below 0.5 or even below 0.2 picoseconds per square root of kilometer. So keep this in mind. More than 20% of all new fibers have massive PMD, and this is not depending on the type of installation. It means both overhead wired fibers as well as buried fibers. Just one example of regarding all the nonlinear effects, how they may affect transmission, and this is really only one of the effects. Self-phase modulation. Self-phase modulation simply interacts with chromatic dispersion, and this may be disastrous or maybe even in a useful way, which is shown here. If we choose the right dispersion domain, the right sign of the dispersion parameter, so in effect the right fiber and the right wavelength, the combined effect of self-phase modulation and chromatic dispersion may be quite a good one. You can see it here, the eye opening increased rather than decreased, which is the case here. And the good news is the plus sign is easy to be achieved. Use standard G652 single mode fiber and use standard DWDM wavelength, then you are here. But still the effect depends on modulation. So if possible, we want to use this effect by proper intelligent modulation. A word on applications regarding 40 gig. Despite the hype 2, 3, 4 years ago, there aren't too many. I think there's only one, which is 40 gig interfaces in high-end routers. 40 gig would be the logical next step in synchronous digital hierarchy, but common thinking today is that synchronous digital hierarchy will die out within the next 10 to 12 years, so this isn't too relevant anymore. Nonetheless, there are high-end routers, Cisco, Juniper, which have these interfaces for good reasons. Huge advantages with regard to link bundling and load sharing. Main reason. I'm not too sure about footprint and power consumption anymore, because interface cards for 40 gig have the same form factor than interface cards for 4 10 gig interfaces. So I think this isn't correct anymore, but this is still the main driver. Well, and then there are some advantages with regard to management, in effect, operational expenses, OPEX. And there's a but. This one. Today, 40 gig isn't cheaper than 4 times 10 gig. It's massively more expensive. Typically, within digital hierarchy, we had a factor of in price of 2.5 between 2 steps in the hierarchy, but the bit rate increased by a factor of 4. So bit rate increase of 4, price increased by 2.5. Effect is bit per second is getting cheaper. we don't have this factor of 2.5 today between 10 gig and 40 gig. We have a factor of 10. A word on Metro WDM and 40 gig. Typically, where is it? Customers expect something from Metro WDM systems. And this is a cost advantage over ultra long haul, ultra high capacity. They expect that these systems are very simple, ultra reliable, plug and play, and if possible install and forget. And they expect something else, which is they should be upgradable. So we are talking in the context of 40 gig, not greenfield installation, a new system for 40 gig, but I am talking about upgrading an existing system which already supports 2.5 gig on-off keying and 10 gig with on-off keying. This will decrease the candidates in terms of modulation, etc. All of this requires very mature technology, cheap components, etc. Whereas on the other hand, today it's not even clear which modulation technology will be chosen, etc. So my conclusion is 40 gig is not ready for Metro, and nonetheless we are offering it in a couple of months. I talked a little bit about the constraining effects, which make transmission pretty much more difficult rather than 10 gig. So some things have to be done. And in effect, everything that's possible has to be done. So we have to use high gain forward error correction. We have to use advanced low noise amplifiers, the ones that were already mentioned, Raman, etc. We have to use this proper dispersion management. So something has to be done to cancel the accumulated chromatic dispersion. We have to use, in addition, we have to use these tunable CD chromatic dispersion compensators, maybe pre-chirp and other things. And we have to use other modulation formats or techniques rather than the old, well-known non-return to zero on-off keying. This would not work properly anymore. So in effect, it will be a combination of all, so using FEC, advanced amplifiers, dispersion management, tunable dispersion compensation, etc. This slide already mentioned some strange candidates for modulation. What's this about? We are not talking on-off keying or binary amplitude shift keying exclusively anymore. Just a slide to explain it. This is what is being done typically today. On-off keying, binary, obviously we have only two states for the symbols. The one is 0, the other one is 1 or whatever. And the other candidates that we are talking now mainly are these. It's not all of them, but some of them where duo binary is a ternary modulation scheme. I think it is well known from power line communications as well. Differential phase shift keying is binary as well, but both states are transmitted using power and where the information is encoded into the phase. And it has to be differential phase shift keying because in the optics we can't directly detect phase. Then one of the candidates for 40 gig that is massively discussed today is differential quaternary phase shift keying. So here we have 4 symbols, so with 4 states of the symbol, sorry. So with one symbol I can obviously transmit 2 bits, effectively decreasing the baud rate on the fiber to 20 gigabaud. And there are other candidates, 8 DPSK, 16 DPSK, etc. And I want to have there are many other candidates, and most of them are combined with either non-return to zero pulse shaping or return to zero pulse shaping with different duty cycles like in most cases 33%, 50%, or 66%, which is then referred to as carrier suppressed return to zero. It can be combined with chirped return to zero, or chirped carrier suppressed return to zero. All of these are different modulation techniques applied to either on-off keying or duo binary or differential phase shift keying. On top we have certain electrical and optical time domain multiplexing techniques. So we can additionally use polarization multiplexing if the fiber supports it. So in total this makes, I don't know, 50 to 100 possibilities, and nobody knows which is the best one for which application. And there are also some exotic variants. Never mind. 2 slides on non-return to zero, return to zero, etc. So this is what we are doing today. Non-return to zero, obviously, as the name implies, between two 1 symbols, there is no return to zero. There is obviously one if some zeros are to be transmitted. With return to zero, again, as the name implies, the intensity goes back to zero. And with the carrier suppressed return to zero, there's also an added phase modulation. With and this was only intensity modulation, so on-off keying or amplitude phase shift keying. And sorry. With phase modulation, we have typically with non-return to zero a constant envelope. This is one of the advantages of phase shift keying. It simply transmits more power per symbol. And the information is encoded into the phase. And since we have to use, differential phase shift keying, we need an encoder, which is a simple device combination, for example, of an AND gate and a toggle flip-flop. And with return to zero, differential phase shift keying, we have still all the pulses are being sent with energy, and still the information being encoded into the phase. Similar, but not exactly the same with duo binary. It's simply another encoding scheme, and these are, well, both the two possibilities for non-return to zero and return to zero. One more slide on return to zero versus non-return to zero. Why are we considering it? Mainly because although today we are using non-return to zero in 99% of all cases, I would say. Return to zero has some big advantages, and is now one of the things massively considered for 40 gig and beyond, of course. And that's mainly it, It has pretty much better PMD allowance. So return to zero would be the technique which gives me the allowance against polarization mode dispersion, which I do not want to compensate. And it also is pretty much more resistant against nonlinear effects, which would occur on long distance transmission. I mean, long distance could cover the regional domain, say 2, 3, 4, 500 kilometers. That's now being called regional, and 500 kilometers would be enough to show some serious nonlinear effects. Mainly 4-wave mixing. So return to zero has some pretty nice advantages, and this is shown here. Polarization mode dispersion mainly leads to something like two-way transmission, or at the receive end an additional echo being received, and obviously this echo overlaps with the other mode, and hence something like this here can occur. By the overlap of the two modes, the combined signal can leak into adjacent time slots, which simply causes intersymbol interference or bit errors. With proper return to zero modulation, there's still some, some space in time left for this dispersion mechanism, and hence there might be no intersymbol interference. This is looks rather simple, but it is really the effect behind return to zero. Well, and hence we have certain possible transmission systems. I will only show a handful of them and will not go into too much of detail. This is the reference, which I call the reference, the non-return to zero system for 40 gig. This is what we do with 2.5, with 10 gig, say, with external modulation. With 2.5 gig typically today is directly modulated for cost reasons. So this is what a 10 gig system would look like, and this is now the reference for 40 gig. I try to characterize this. The longer these gray bars are, the better it is. So relatively poor behavior with regard to chromatic dispersion, relatively poor behavior with regard to PMD. But for example, low hardware effort, which is good, long gray bar, and obviously, since it is exactly the same technology, it can be used for upgrades of 10 gig on-off keyed systems. This is relevant. If this isn't there, I can't use the technology for upgrading existing 10 gig systems. So let's have a look at the contenders, as I call them. This is carrier suppressed return to zero, existing modulation scheme for 40 gig. Here we have the addition of the carrier suppression, simply by means of another external modulator, which is used as a pulse carver for proper pulse carving. And we can see chromatic dispersion, no big change. PMD, the allowance massively increased. No, and nonlinear effects as well. And these two only decreased a little bit. Hardware effort, that's clear because we have an additional component. And the upgrade is decreased a little bit, the possibility, because this typically doesn't support 50 gigahertz. So if we are to upgrade a 50 gigahertz system, it wouldn't work. I will quickly go through the other ones because I'm running out of time. But I want to mention in particular this one. Differential phase shift keying, typically combined with return to zero. So in this case, carrier suppressed return to zero. Big advantages with regard to PMD, since it is a return to zero, with regard to OSNR, because DPSK typically has an advantage of plus 3 dB. With regard to nonlinear effects, again, it is return to zero. Hardware effort, well, we have this strange receiver, which contains some potentially expensive components. But what's this? No gray bar anymore. It can easily be shown that DPSK doesn't work as an upgrade technology for systems where there are also on-off keying channels. So, nice contender doesn't work as an upgrade technology. Pretty much the same with DQPSK. Hence we have a matrix, a summary, on-off keying, including, by the way, carrier suppressed return to zero. This is still on-off keying. Low to medium effort. Pretty good distance capabilities, and yes, it is a candidate for upgrades for 10 gig on-off keying. Pretty much the same for duo binary. Completely different with DPSK and DQPSK. They can have very high distance capabilities, and in effect it's these which are discussed for multi-thousands kilometers transmission systems, but then it's green field installations. No on-off keying on adjacent channels. So they can't be used, as I said, And there are some others which I didn't even mention. Same in a picture. So we are starting here, and we can split it into the characteristics of fiber. And if we say we are in the metro to regional domain, so in the lower half, then we can relatively easily identify two contenders, which is duo binary and return to zero, which means carrier suppressed return to zero. And these two, well, are relatively useful for upgrading metro WDM systems, which was the original question. So we'll have a solution. Yes, to be honest, it is an OEM technology. It is already tested with our main transmission gear, the FSP 3000. It was live demoed at the CeBIT this year in Hanover. And it will be tested in the German Viola testbed or network mid of this year. And, big surprise, no. It is useful, of course, as an upgrade of existing FSP 3K installations, reusing the filters, the amplifiers, the dispersion compensators, etc., and of course, enabling upgrades of existing 2.5 gig, 10 gig systems. Well, it offers the usual suspects of interfaces. That means OC768 transponders and 4x10 gig max ponders. And yeah, this is the big surprise. It is carrier suppressed return to zero. So one of the candidates which could be identified as a potential upgrade technology. The very good thing is it works really pretty good, carrier suppressed return to zero. In effect, it has 9 picoseconds PMD tolerance, whatever this exactly means. Our own Metro 10 gig gear has 10 picoseconds, not much more. So this system supports almost the same PMD than our 10 gig gear. Same with the OSNR. Our 10 gig transponders do require approximately 17 dB as well in the best case. And also with regard to chromatic dispersion, because this allowance window of 400 picoseconds per nanometer is approximately the same that you can find in typical metro systems. What does it mean? This is compatible with, well, our existing 10 gig links, but these are pretty typical for existing metro 10 gig links. So what is it to say? This is a useful technology for upgrading existing 10 gig. And that should have been the end of my talk. Thank you. Any questions?
Please come on.
Oops.
The price. You mentioned the 10 times handicap.
It's not 10 times that much, but it is by now it would be more than 4 times more expensive than 10 gig. So I can't exactly say what it'll be like in say 9 months from now. My guess is that 40 gig will not get dramatically cheaper. And that's because we will see that there's... I'm not convinced that 40 gig in routers is really a killer application, as we say. I guess the whole community will switch to 100 gigabit Ethernet, and then there will be no 40 gig anymore. So, and that would obviously influence components costs and hence systems costs. Thank you.
Thank you very much. Our next speaker is Kees de Laat. Kees de Laat is an associate professor in the Informatics Institute at the University of Amsterdam His current research area include optical switch networking to optimize internet transport of massive amounts of data, especially grid applications. Kees de Laat is well known. He's one of the leading heads of the Grid Forum Steering Group and also in GLIF, the Global Lambda Integrated Facility.
Well, I didn't get it over my ears yet. My ears are strangely positioned, I guess. I'm a big head, so to see. Yeah? This looks good? Okay, thank you. Okay, this is the test to see if I have the full picture. So I'm dropping in for somebody who could not make this session. But I've done that before, so I should be fine. So my name is Kees de Laat. I'm from the University of Amsterdam. You may wonder what all these affiliations mean actually, but they are funding agencies which fund my group, and the font size is proportional to the funding I get from these funding agencies. So you can infer a little bit. So at the bottom is Dutch Science Foundation, who pays actually my Grid Forum Steering Group travels. I want to talk in this half an hour about Starplane. That is a project which we came about a year ago, 1.5 years ago, and is about having a photonic network which is modifiable in the photonic level, not OEO, and have grid. I don't know, this is not sticking. So, and have grid applications directly influencing the topology of that network. Starplane is a Dutch Science Foundation funded project with major contributions from Surfnet and Nortel, of course. The vision is to allow part of the photonic network infrastructure of Surfnet 6 to be manipulated by grid applications to optimize the performance of applications which are running on it. So applications will be empowered to, within certain constraints and within only for certain band of lambdas, to really say, okay, for the next 10 seconds I need a tree structure, or for the next 20 seconds I want a ring topology, because we need to do next neighbor communication in the distributed application. Starplane will use the physical infrastructure provided by Surfnet and the distributed supercomputer DAS3, that's distributed ASCII supercomputer, on which I will also spend some words, because it's quite important to see how these clusters can interact with. I am losing my voice. I had that this morning, so I probably want some water. And it is important to see how the clusters can interact with that network. So the novelty of this project is to really give the flexibility directly to the applications and let them see the network as just an extension of their internal bus system or their disk drive, and just, arrange it as they want. If I take a step higher and look to scheduling and grid co-location, to the grid co-location problem space, then you see that what usually used to be done is a lot of CPUs. Where is my CPUs? Where are my CPUs and where's my data? Co-locate them and schedule them, and there's a lot of research on this. And the network is usually seen as, such a dirty, unreliable constant in the functional, so in the functional which you want to optimize. But you cannot modify it, and it is unreliable, so you try to use it as little as possible. But now you get into a phase where you can really, this is now also a function. You can set what you want, and it will provide it to you. And so you get now a three-dimensional space where you look for your optimal scheduling. So it opens up a complete new area of research. Starplane applications. For all these networks there are always questions, why do you need it? I mean, what's your killing application? These are of course the usual scientific applications, which are not at all killing. These are, the e-science, e-health, high energy physics, astronomy and so on. I can say two things about these applications. If you look to networking over the last 10, 20 years, then about 15 or 10 years ago, the high energy physics community started to understand that they were creating huge problems by producing all the data and needed to fork that out over the world in the grid and needed also a network infrastructure for that. So the high energy physics community was aware of all of this 15, 10 years ago, created all the projects and have now their tier 1 network in place. The astronomers, the astronomy community came about this idea about 5 years ago with their EVLBI. Wouldn't it be nice to not ship tapes but to put them on the network? And what you are now seeing, so now the EVLBI work is coming online, and what you are now seeing is that life sciences is now where the astronomy was 5 years ago, and e-bioscience applications are also coming up. So you see that happening, and one of the big applications we will look at is Carry, is a project in the Netherlands where we use software correlators. Because of time I will not say too much about it, but please ask me a question afterwards. So this is the network in the Netherlands. It's a dark fiber based network which SurfNet currently has. All these lines here are dark fiber, so SurfNet can touch every customer of them with dark fiber and put DWDM equipment on top of it. They have 180 between quotes customers, universities, academic hospitals, schools, research centers, and so on. So the user base about 750,000. SurfNet now owns about, or IRU, about 6,000 kilometers of dark fiber, which is nice if you compare that to the railway infrastructure. It's also a nationwide infrastructure. It is about 5,000 kilometers of railway in the Netherlands. So you see that these nationwide infrastructures have the same scale. By the way, you see that the Netherlands is not that big. It is about 2 milliseconds round trip time on dark fiber by 3 milliseconds round trip time. So everything is for US people more or less in a metro area, which also gives you a measure that the Netherlands is apparently 6 square milliseconds big. This is the common photonic layer in SurfNet. So the Netherlands is divided in 5 rings, and each ring, so on this dark fiber, can carry about, currently with CPL1 version, about 36 lambdas. Some of these rings are now upgraded to another set of filters so that it can actually carry in 9 bands 8 lambdas of 10 gigabit currently in total. So that gives you 72 lambdas, 10 gig each, and they are moving to it. So the capability for 40 gig is around the corner as far as I understand it, but probably same as nuclear fusion, it is always around the corner. Here is the green ring. This is an important ring. This is the ring where 4 universities are located who are collaborating in this distributed ASCII experiment, and which will actually run this Starplane project. So the Starplane project is about having dynamic, on one ring, dynamic add-drop multiplexers or photonic device which can really, pick lambdas out of a ring, out of a fiber and put them in another fiber, and connect that directly to computer clusters, such that the computer clusters, here you see the CPUs, the green boxes, can signal to the network operation center of SurfNet. And mind you, you are crossing a boundary here. You are going from the untrusted university environment into, the trusted NOC center, and then the NOC center automatically should rearrange the topology by modifying devices in the SurfNet in that ring for the purpose of this experiment. We will get for this experiment 1 band of lambdas, so 1 band of 8 lambdas. Not all of them will initially be lighted, but enough to do quite interesting experiments. And basically the picture looks like this. We have CPUs here. They go into a switch on which I will spend a few more words in a few slides. And we have then 8 times 10 gigabit Ethernet LAN PHY going to a box here which is actually then just translating this light by OEO into a lambda, into a colored laser, and that colored laser goes photonically through the system, and depending on the configuration of wavelength selector switches here, it is dropped off at one of the other locations. And actually this is a highly logical picture. The true picture is that the wavelength selector switches are concentrated in Amsterdam, and via the ring the lambdas reach the other universities, Delft and Leiden. We have been doing a tender which was recently completed, and the contract was awarded. And the clusters look now like this. So the contract was awarded to Cluster Vision, and you can find, if you wish, the press release here. But logically, the clusters look like this. You have a number of blades, as usual. On one side, we have chosen to go for MiriNet, 10 gigabit MiriNet. This is MiriNet protocol, what is running on the purple lines. This goes into a MiriNet switch, and the MiriNet switch will get an 8-port 10 gigabit LAN-PHY Ethernet card, and those 8 will go into the OME 6500 from Nortel, where then the colored lasers which sent into the core network are located. So there is an OAO from here before you enter really the dark fibers of, the not so dark fibers of SurfNet. And actually we will have 40 nodes here, and other sites will also have a little bit more. There's also, of course, a standard network which is based on normal gigabit Ethernet switches and 10 gigabit uplinks to go to the head node and to go to the local infrastructure, and this will be implemented with Nortel's 5530 stackable switches. That's the cheapest way to get there. This gives you a little bit that we have heterogeneous clusters, that there is a lot of CPU power, a lot of disk space and so on, so these are interesting numbers, but I advise you to download the slides to really dig into them. But it will be quite an heterogeneous but very capable environment, which will be able to create and absorb hundreds of gigabit of data. Here is this picture. You see the DAS3 cluster with MiriNet 10G and MiriNet protocol. So this piece is running the MiriNet source routed networking transport. And here you will get a mapping from the external MAC layer, so the MAC addresses it sees here on Ethernet, to internal source routed, how do I reach the destinations and vice versa. And this is then the translation from LAN-PHY to colored lasers, and here you are at the optical airdrop multiplexes in the CPL environment in the SurfNet core. This is a kind of logical picture of how these wavelength selective switches work. They go in, sorry. So they go in, there are 5 fibers, and from each fiber, the entire ITU grid which is in there is projected here on a diffraction grating, so a grating, which puts from every fiber the color here on a different MEMS device mirror, and then depending on which mirror bounces it back in the correct angle, those colors will reach then the central fiber and go out. So it can pick any color from any fiber and then put it in the outgoing fiber, and as such select the wavelengths you want to have in the outgoing fiber. And these, the switching times technically for these things are of course 10 milliseconds, but changing colors on rings is kind of complicated. So what will make Starplane possible? Wavelength selector switches is a very important component here, of course. Just on the photonic level, being able to change the topology of the colors. It is made possible because we get a kind of sandbox. Mind you, the ring where we will run these experiments on is also carrying production networking of about 5 other universities. So if we do something wrong there, then I will get famous in the Netherlands, but I may not like that. So The fact that we can sandbox it and confine it with filters in one band is crucial here, or we would need another ring of dark fiber just to do star plane. Also, the sandbox is important because the controls currently in the telco invested software implementations to bring up or bring down a lambda mean that it takes 2 minutes to 20 minutes to bring up a lambda on a ring, because all the amplifiers and filters want to adjust themselves if you bring them up and bring them down, while we want to go to sub-second provisioning, and that means that we need to be able to turn off or make sure that we are fine anyway without retuning. We need to turn off some of these securities or modify them, and we need to do that in the sandbox. Optimizations for these controls is what I talked about. Another thing which is important is the electronic dynamically compensating optics, or the EDCO modems, which Nortel has produced over the last years or developed, and which are now coming into production. These modems are capable of running on fiber which do not have dispersion compensation. So what they basically do is the modems strain on each other and send packets like, I think that the dispersion is this, and this is the way I send the packet. And what they basically do, these modems, is they try to estimate the dispersion function. Then they invert that function and they convolute that electrically with the train of zeros and ones you want to send out, and that way they modulate the laser, so with amplitude and phase, and then they send that out on the fiber. So what you normally would send out on the fiber is a nice pattern, but on the other end you would get a wobble. What they do is they calculate such a wobble that on the other end you just get a nice pattern. That's what they basically do. And that is important, because if you flip such a mirror, it may be that one of the colors would go from one university to the next one, and that one has to go much further along and would encounter a different dispersion. And so if you want to do these dynamic changes, you need also to be able to have modems which can dynamically adjust themselves to different dispersion effects they see. And of course we will need a lot of traffic engineering, because we will have 4 or 5 clusters on different locations with lots of CPUs, and we may want to have all kinds of patterns. So I have some slides which show that. We will have 4 locations: the Free University, University of Amsterdam, where there will be 2 clusters factually, in Leiden and in Delft. And you can have that part of the cluster in the UVA wants to talk to part of the cluster at the Free University. So for this is relatively trivial, but you would probably need a VLAN or just, a connection. But you can have more complicated cases here. And mind you, this is the whole optical photonic network is just a black box. It are just, extended fibers. So there's no intelligence in there apart from, so not on the data plane level. It is just a flat layer 2 network if you don't take care of that. But it might be that you would get, because you have a ring, a kind of ring infrastructure. So spanning tree would turn off a link here if I would ask for this topology. Same here. You may have this kind of connectivity, but you may want via the same connectivity 2 different grid jobs to talk, and then you need to somehow separate some of the traffic so that not one grid job is influenced by another grid job. So that needs actually VLANs, of course. Here are more complicated, that you have even different grid jobs wanting different patterns while sharing parts of the same cluster, so you can make it quite complicated. And given that this is all just flat layer 2 stuff, we need to do traffic engineering in terms of VLANs, trunking, and so on. And that is really an extensive part of this project, apart from, of course, the control plane to set up those lambdas. So small intermezzo. There are also, of course, risks here. what we have today and what we want to avoid. So this goes back to a few pictures I took when my family and I were making a trip to the Grand Canyon, and at the camping ground washing facility we saw this picture, which is why it's not coming up. Hey, I see it on my screen here. Okay, I try one other way. So I put this on mirroring. And now I put it this. Huh? Yeah, so I don't know. Okay, this is Microsoft trying to easy my life, I think. Okay, but I'm resourceful. So you see here I found such a terminal running also SurfNet, you know, at the camping ground washing. 3 easy steps. Click the start button, insert money, and for some money per minute you get some, and then you can surf the web. So you can check your email, for example. So just very easy, actually refers to the token-based networking concept we are developing in our group. But we want to avoid this, which I also found there. So I need to make sure that whatever we do with Starplane, we are not affecting the other production traffic, which is running through the same filters, through the same wavelength selector switches, and through the same rings. Although for part we can avoid that with the correct sandboxing techniques. So what do we need for traffic engineering? We need VLANs, we need trunking, we need spanning the tree modified probably. That's one of the capabilities. Just modify spanning tree, or the new IEEE work which is happening, Mac in Mac techniques. Source routing modified possibly. That's also possible. The MiriNet stuff builds up reachability and creates source routes for every destination MAC layer address, so playing around with those tables may be an option. We need policy interfaces. We need to make known who may, under what conditions, why use part of the photonic network. And that means also AAA interaction, and if you want to really roll this out, have a dynamic photonic network, you need to connect to, so you need to authenticate who is putting the question forward, so you need to connect to Ethereum and Shibboleth. We have a poster on this project, which is just here, the last poster, if you go totally at the end of the list of posters, so please visit and find one of us to explain you more detail if you have questions. You see here also a little bit the network topology as it will actually be. But there are still a few key issues. So how do you describe these networks and how do you allocate them? And that are the last few slides. So if you look to the infrastructure we have, for example, in Amsterdam, having MEMS devices for STAN, clusters, tile displays, all kinds of infrastructure. And connected to the UVA, this is together with Supercomputer Center, this is Netherlight, routed internet. This is a complicated picture and can get much more complicated. And certainly if you want also to describe glyph networks and so on. So we went into looking into techniques which are used in the semantic web to describe relationships, and we took this way of describing relations by subject, predicate to object as a way to describe what interfaces are, where they are linked to, and so on, and describe topologies and resources using resource description framework. So we have created a network description language, a way to describe network resources using RDF. We have parsers, and here you see a kind of example where interfaces, what it is and what it connects to, or what some of its properties are. This, for example, you should not even try to read it, but it should give you confidence that there are now tool sets created by people at Sarah and my group which can extract from devices the configurations and infer from that what the current states and the topologies are, and create then an RDF file. And the nice thing is you can have a web of RDF files. So one RDF file in one domain can point to RDF files in other domains. So every domain, so every administrative domain can keep its own RDF files under their own control, and in that sense it scales. So here you see an automatically generated Netherlight RDF file. Here some paths where you see really, up to the port level, described and where it is connected to, and what its name is, and so on. But we have also tools which make plots from this, and for me as manager this is always convincing. If you read this stuff and it creates a plot of the true infrastructure as it is connected, then you get the feeling that indeed, well, you can make nice plots, but you can also make path-finding algorithms which can find then their way in this hybrid infrastructure. And that's part of the work we are currently doing in Cliff, defining this framework and testing it and rolling it out and bringing it in the Cliff. Here you see also based on RDF. So with the tool they got out of the SurfNet equipment the whole topology, put it in RDF, and they used the tool to plot part of the SurfNet network, and they got really out what is in the field. So this gives a kind of sense that it is possible to get the topologies described and then to make them available to other domains to do path finding and publishing of topologies. So there is also a poster on that on the same board, so I advise you to visit that, but we think this is one of the key technologies to get grip on those topologies. There's another issue, how do you book resources and so on. Basically you are virtualizing and turning your networks in a kind of service-oriented architecture in a web service. Last year one of the people in my group has, Paolo Grosso, has done some work on that, created a web services interface, defined the primitives to ask via the web service, give me the possible passes and give me a pass, reserve it, and so on. There's also a poster on that we had at Supercomputing, and she's in the room, so you can also ask her. This brings me to the end. Thank you.
Thank you very much, Kees. I'm sure we have any questions. Dimitrios.
I have one comment and one question. I'd like to know how do you do source routing with the MAC addresses with the MirNet nodes. You said that when you connect.
So maybe I know already what you try to ask, because I had the same question when I visited MirNet. They do a kind of source routing translation in the 10 gigabit Ethernet card for every port. So they built up the source routing for every MAC layer address from the inside out. So,
so it's just a translation, it's not a routing.
No, I mean source routing means only that you have a packet, but you prepend bytes which tell at the next switch I want this packet to go out at this port, and the port number is in that byte. So if you do have a source routed network, you need to prepend these bytes so that the system knows where to get the packet out, and you need to pre-calculate that for all possible routes and put those tables in the NICs, because the network interface cards needs to do that source routing.
So is this done on the, let's say, Ethernet device, or is it done in Fabric?
Well, it is done in every MirNet NIC, and the Ethernet card in the switch needs to do it also for every destination inside the MiriNet network. All the MAC layer addresses which are on the outside of that Ethernet switch need to be broadcast to all the NIC cards on the inside, so that they can build also, that they know also, okay, if I want to reach that MAC layer address, I need to prevent these bytes.
So it's a specific purpose Ethernet switch, I mean, to match the MiriNet needs.
The MiriNet switch is not an Ethernet switch, it's a MiriNet switch.
And another comment I'd like to make is regarding the traffic engineering, let's say, dream or objectives with regard to the Ethernet. Do you believe that this kind of, let's say, demands we have from a protocol like the Ethernet, the traffic engineering is like trying to build again the IP routing on the Ethernet approach? I mean, you need traffic engineering, you need other activities like where you have very simple protocol like spanning tree to do routing, which has only one topology, which is the star topology, no matter what the physical topology is. Now we're trying to build an ad hoc topology, it's a routing protocol, and we haven't yet defined if it will be destination-based or a source-based routing. So it seems like we're trying to devise again a routing protocol, a topology, a networking topology for which substitutes the IP and does the same thing.
Maybe you are confused when I say source routing. That is not true routing.
You said that we
need traffic engineering, but that's a different thing. And I think with the combination of trunking, so where you have parallel Ethernet and where you can do VLANs, you get already quite far. If you do two-layered, so Mac Ethernet protocols and newer protocols, you could also do a lot of the traffic engineering we really need. But that has nothing to do with routing. If you want to go to routers, and if you want really to implement this with routers, it would cost much
I'm trying to say that if you have a big topology, you can do traffic engineering with VLANs, yes, hop by hop, I mean, every time. But I mean, having to deal with a big Ethernet network, it's very cumbersome to do that on every hop by hop. And I mean, there is not a big engineering tool to do that in a scale.
No, that's exactly that's the research.
Oh, okay.
Jerry.
I was just gonna add that there's some folks in Creo in Stockholm who are working on the GELS protocols to do the label swapping in the Ethernet layer. Mm-hmm. So you can get things that'll scale better than just flat VLANs. Yeah, somebody will still use it, but you're right. ITF kind of turned their nose up at it.
Okay.
Okay, thank you. I think we stop here. If you have more questions on this very interesting topic, please, Case is still here. Then it's lunchtime, and after lunch, please do not forget the feedback request. You can do it online.